All right, good morning to everybody. Um, Welcome to the next edition of our workshop. And today we're going to be learning how to perform statistical analysis using R. I hope you can hear me well. Give me a thumbs up if it's clear and everything. So that I know that it's okay. Cool, that's great. All right, so we're gonna have a very fun class today. I'm very excited because I like statistics. Just that I don't get to teach statistics very often because it can be very niche and not a lot of people either want to learn or want to perform be very customized statistical analysis. But it's going to be a very fun day today. I'm going to go through a little bit on data structures, what sort of variables you have to perform statistical analysis. We'll go through the different tests, one sample, two sample tests. We will go through parametric, non-parametric tests, how to test for all these assumptions, especially for parametric tests. And then we'll look at multiple sample testing. We look at ANOVA. We look at different sort of non-parametric tests for that. And then we will be doing some other variations like a contingency table, test for independency, chi-square Fisher's test, and then we will end off with a correlation test, right? Abby, you said that you do perform linear regression. I will put a link to ways to perform linear regression in R, but I think for the most of us, we tend to go with correlation tests because I don't see a lot of people working with prediction models. Well, not from basic scientific data, and at least. So if you have any questions about linear regressions, feel free to ask me, and I will be more than happy to answer any sort of query. But I'll give you the link later on in the links table. All right.
Okay, thanks.
Yep. So make sure you have R and R Studio installed on your computer. It's very important. And make sure that you have that CSV file that I have emailed you. It's exondata.csv. Somewhere on your computer. Make sure it's accessible. So you know where to find it. If you haven't done so, go ahead into Etherpad and check in. This is just to make sure that you are able to access the Etherpad and you're able to type in something. I think Pat and Shinya, you haven't done so, just to make sure that you are able to see the details over there and click on the links. All right. This lesson has been recorded 5 minutes before the start of the class. So we will upload the video again onto YouTube. So if anybody wants to review the video, feel free to do so. If any of your friends wants to learn or wants to follow along this workshop, go ahead and disseminate. It's the link is what do you call it? It's not public. What's the term? Unlisted. So you need to provide them with the link. They cannot really just search for CDN statistics to search for this class. So you have to give them the link. All right. Okay. So so in the Etherpad, we are going to paste all the codes for today. There's not a lot of people here, so feel free to unmute yourself and ask any question at any point of time. I'll be more than happy to answer your questions and your doubts as we go along. And any sort of resources and exercises we will be doing here in Etherpad as much as possible. All right. And here comes your first exercise. All right. So I'm going to paste the first exercise into the Etherpad, and it's a very simple exercise just to make sure that all of you are, this one is all of you are more or less versed with, data import in R. And what I want you to do is to, again, start up your R Studio, open up a new R script, and simply import that Exon data that I have provided you. All right. One caveat though is that there is a column which with a categorical variable. Convert that into a factors. Right. It's a very simple code. It's just one line, but give it a try and see if you can get that data imported into R. I'll give you about 2 minutes. Okay.
Sorry, what was it that we were supposed to do with the data once we've imported it?
All right, just save it into a variable called dat, D-A-T, and that's it. And then
Oh, okay.
I'll explain to you, or we'll go to the data and then see what are different variables there are in the data set. All right. All right, that should be a simple one. I'm gonna go ahead and share my screen right now. And I'm gonna show you my RStudio. I'm gonna do this fresh with you. Okay, hope you can see my RStudio right now. So I'm gonna open up a new R script. Again, this particular course assumes that you have a basic knowledge of using R. So I'm not gonna go through with the details, but if you're not sure on how to do certain thing, you can copy and paste the code that I'm going to put into Etherpad, or stop me if you're unsure what I'm doing. All right. All right. So I'm just going to quickly save this this R script. I'm going to call it 6stats. Just put it into my home here, and I'm going to create a new variable called dat, and I'm going to use read.csv. This is a inbuilt function with R. There are other functions that comes with other packages like read.r. You can use that. I'm going to use read.csv, and my data is simply in the home folder. So it's actually just here. If your data is somewhere else in a different directory, make sure you provide the path to the CSV file. And I'm going to switch on strings as factors as true. Right. The reason why I want to do this is because I have a column with 3 different genotypes, and I want to convert this from a string variable into a factor that will make the plotting and the groupings a bit more easier later on. Right. With other packages, you sometimes don't get this option. So specifically for this, I prefer read.csv function to import. Right, and I'm going to run this again. On my computer, it's Control Enter. On a Mac, it's Command Enter, or for Command Enter for Mac. Right. So if you have that, that is the straightforward answer for this particular exercise. A simple one. All right. So let's look at our variable. So we can head our data. And
first,
yes, Abby.
do you mind if we didn't? I mean, I think I've uploaded it fine and turned it into dat, but I don't know if I've done this strings as factor thing.
Yeah,
I'm not sure.
That's a way to check. So which function they use to import? Do you use the same one, or is it? Or do you use a different?
To be honest, like you can just, once it's in the right file,
you
can just literally ask it to open.
So
and it opens as accent data, and then I just turn that into dat.
So you mean like clicking on here, clicking on here. Okay, let me see. You see like that
data set.
Okay. So yeah, this is another way to import. I think we went through on our second or third class.
It actually uses read_csv.
Yep. That is fine. Let me see. They don't have an option for. See, right now you can actually preview the column. Genotype is still a character. Again, which is fine. If you are fine with having the first column as a character, it's fine. Just that for this purpose, character will not show you or will not categorize your values into groups. So
okay,
for
I'll run your script. I'll delete that and run your script.
Either way, I'm fine with either way. This is, I guess, a lot of people also like to use this when I teach, new classes or new people. I do mention about this importing. This is fine if you routinely do this importing, frequently. For scripts or for workflows that you do very frequently. If you know or once you have imported that data using that import data, copy the code and save the code in a script. That is my recommendation. So you learn the code as you go along, if you understand what I mean. Yep. So either way, as long as you have the data in R, I'm fine with it. Okay.
Okay, thanks.
Okay, so if you had this data and look at the first 6 lines, you can see that we have 3 simple columns. This is an arbitrary data. It sort of represents the sort of work that we do, but the values here are arbitrary, is generated, all right? We do have a column that says genotype, we have another column that says exon length, and a third column that says exon branches. And this is printed out by using just head function. This is where I'm going to start by sharing with you the different types of data variables. All right. So very quickly, there are 4 types of variables that you can have in any sort of data set. You have nominal data. These are strings or factors or groups that has no ranking. There's no inherent order to this particular data. For example, our genotype here is actually a nominal data because you have 3 different genotypes and neither one has a particular rank, right? You can also have the same categorical values, but in an order manner. For example, date, time. These are ordinal data. Right? The next 2 are numerical data. The first one is discrete data. This is where you have a numerical values, but they are discontinuous. Meaning, if you take 2 values which are side by side, there is no value in between with these 2 values. For example, IQ. For example, if you let's say take 170 and 171, there is no such thing as 170.5. It's discontinuous, right? On the other hand, you have the continuous variable, again, numerical, but in between 2 values, there can be sub values. For example, height, right? For example, 175 and 176 centimeters, you can have any variations of decimals in between. It can be 175.1, and even this, you can even go lower to get better resolution of that value. So this is example of a continuous variable. All right. So in our case, exon length, the second column here, is an example of a continuous variable, and exon branches is an example of a discrete variable, because again, you cannot have an exon with 3.5 branches. It just don't make sense. All right. So why is this important? Because the type of variable you have will determine the type of statistic test you're going to employ, right? For example, if you have a categorical variable, you can't apply, a T-test or ANOVA test, because these are they do not take up any continuous values or numerical values. Okay. Also, the distribution of your data is very important. You need to know whether your data is normally distributed or not. This goes for both continuous and discrete. If there is a reason to assume that there is normality, then you can go with parametric tests. This sort of tests have some assumptions. I'm going to show you what some of the assumptions. If assumptions are not met, you have to go straight into nonparametric tests. I'm going to show you the difference in a bit. Right. Another thing that I want to mention to you is the format of your data. All right. Again, I mentioned this quite a bit of time. If you're in Excel and you start to tabulate your data, you have the liberty of creating a new column and putting your data in any order that you want. That is fine. Right. With programming languages, you have to have a little bit more discipline of how your data is actually presented. Right. The best way to present your data is when each of your columns take up a particular variables or a value that you're trying to quantify. Right. In this case, this is actually a very simple data and it's well formatted. Right. Because each column has this particular meaning and a particular value to it. Right. I give you an example of a data which is less tidy or less well formatted. And for example, you have, let's say you're doing a time point experiment, right? And you're, let's say, measuring exon length for 4 different times, for example. Some people may choose to kind of put, let's say, 1 hour in a particular column, 2 hours on a different column, 3 hours on a different column. So this is where, each column is no longer variable, but this is an observation, 1 hour. This is like a measurement, all right? So this is, for tabulation purposes, this is fine, but with, to do statistical tests in R or even other programming languages, it's best to sort of tidy this thing up and put all of these values into one single column. So for example, if I were to have, if I were to measure exon length based on a particular time point, what I would do is to have a single column just for time point and tabulate, let's say, for example, this particular value here is for 1 hour. I will have that column specify this value to be 1 hour. So it's A, 1 hour, and the value, right? If you have another data point at 2 hours or 3 hours, it will take up another row, all right? So you have multiple rows for, let's say, for the same genotype, but you take it different measurements for the different time points. Same goes if you have replicates. So if you have 3 replicates, right, you can specify first replicate, second replicate, third replicate if you want to. Replicate is a little bit more easier because you even if you don't mention replicate, it's understood that it's coming from the same genotype and time point, right? So formatting your data is very, very important. And I have given a link in Etherpad on how to tidy up data. I think I showed a couple examples before, but if you have any questions about how to sort of tidy your data up, it's actually a very, very good practice. It saves you a lot of time in the future. All right, cool. Next, just a small bit I want to mention is to know your comparisons. Later on, we're going to do some hypothesis testing. We're going to formulate some questions, hypotheses on our statistical test. So know what are your predictor, what are your groupings, and what are your outcomes. Again, outcomes, the type of data of your outcomes determine the test that you're going to perform. All right. So let's go straight into, so basically just quickly write know your comparisons. Okay. So let's go straight into basic statistics, how to perform basic statistics in R, right? So what I mean is that how do you compute mean, median, standard deviation, and so on and so forth. I do recommend this function called summary. I'm pretty sure a couple of you have already, familiarized with this particular function. And if I go ahead and run summary into the console, what I'm going to see is a summarized form of my variables. So each of the columns has been summarized. If it's a factor, in my case, genotype is a factor, it will spell out all the different groups. So I have A, B, C, and the number of data points for each of these group. If you have not converted into a string, then what it's going to tell you is you have 3,000 character values, but for this particular column, and which is fine. Again, this is all fine. There's nothing wrong with that. I'm trying to show you here that there's actually 3 groups in this particular column, right? You also have summary of exon length. Yes, Abby.
Sorry. So if I did what you said, so that's fine. But if you don't open this file as you did with strings as factors, and then you obviously do this and you're going to get 3,000 for the genotype. Is there a way afterwards to
of course
fix that column?
Yeah, I'm going to put a note here. So later on, I'm going to give you a link on how to easily convert strings to factors. It is fun. This is always fun. To be honest, I don't typically import data as factors typically for this example. But then there are ways that I use to actually convert all these strings into factors. I'm going to show you one package which is part of the tidyverse package. You don't even have to install anything else. It's already installed if you have tidyverse, and you can convert any string into factors very, very easily. All right.
Okay, thanks.
Okay. Yeah, it's very convenient to kind of like switch back and forth, and also be mindful of your data type, because sometimes if you have a factor and you're trying to do some sort of filtering and conversion or mutation of values, do check your new values or check your filters before you assume that it's fine, because factors are a little bit more sensitive. They're treated as a very specific sort of data type. So be mindful of factors. Okay, so exon length and branches, you have a couple of statistics. You have the minimum values, first quartile, which is the 25th percentile. You have the median and the mean, so standard values, 75th percentile, and the maximum values. So these are very straightforward summaries of your statistics. If you wish to extract each of these values separately, you have individual functions for that. For example, mean of the mean function actually calculate the mean of a particular variable. The only thing is that you now have to specify that particular column that you're trying to calculate. For example, if I want to do mean of exon length, I have to use this operator $exon length like that to calculate the mean, right? I know I haven't mentioned this dollars thing previously because this is one of the ways to extract information from a column. What it means is that you're using this dollar sign to specify the variable or the vector that you're trying to extract, and then it's followed by the name of that column. Right? You can do this the same for exon_branches. It's going to give you the same sort of statistics. Right? So this is the mean. For example, you can also have median, that $exon length. Going to run this, you can see that you get a value. If you want to do 75th or any percentile, that doesn't really matter here. You can do quantile, that $exon length, and by default, I think by default it's 25th percentile, but you can change this to, let's say 0.75 to calculate the 75th percentile or 60th percentile. So this is all up to you, what sort of quantile you want to calculate. Okay. Two more, standard deviation. This is quite standard. Standard deviation calculates the sort of the spread of the distribution of your data set from the mean, and then you have another variation called the variance, that $exon length. Okay, all different ways. So variance and standard deviation are very similar, just that standard deviation will square root this calculation. Do I have no, I don't have a link to. It's a very standard formula to calculate standard deviation, but standard deviation has its square roots, the values, so the values are not too extreme as compared to the mean, whereby variance actually remains at a square value, so values are very big. So if I do variance, it's about 1,000, 11,000, whereby standard deviation is about 100, which makes more sense to the mean that we have. And also variance has an additional penalty for degree of freedom. So the numerator actually minus by 1 details, just small details, okay? Okay, so these are the basic statistics that you can actually compute with RStudio. Very handy to very quickly summarize your data. One problem that I have with this sort of statistics is that it summarizes the entire column, and it doesn't tell you how the statistics actually compare between each of your groups. You cannot assume that the mean applies for every single groupings that you have. So A, B, C, do each of these have the same mean, or are they different? Right. So that's why I try to do a little bit more than just looking at the basic statistics. So I do a little bit of tidyverse manipulation transformation to calculate mean and median. So I'm going to show you how to do that. But first, before that, let me just copy and paste the code first, because I tend to sometimes talk too much and forget to paste the code. All right, so the codes are all there. Today's codes are going to be very simple. It's not going to be too extreme until we reach probably like the plotting part. So go ahead and load your tidyverse. I hope you have tidyverse already installed on your computer. And we're going to use a couple functions that we have learned before. and these are very, very powerful to do group-wise summary, right? So I'm going to start. You can follow along with me if you want to, or you can wait for the code at the end of this section. So I'm going to start with the det. If you're not familiar with what this is the pipe. I like to use pipe a lot, and I always advocate people to use pipe because it makes your code much more readable, right? To edit, just to read your code, what you're trying to do is actually much more easier, right? So what it does is to kind of transfer the data from before the pipe to the next function, to the first input of the next function. So what I'm going to do is to take that and group it first. So function is group by, group underscore by, and apart from the data which we have specified, we want to group it by the genotype that we have as such, right? This just basically groups the data in the background. It doesn't do anything. You have to then provide your next set of code to perform your operations on each of these group. So what I'm going to do is I'm going to summarize my data. This is a tidyverse specific function, and the input will be your computation, like what sort of summary you want to perform. For example, mean. I'm going to do mean and standard deviation. That's an example. And we have to create a new columns for these new variables, right? So I'm going to create mean length, and I'm going to then follow by equal sign and write down the function that you're calculating. So it's mean of exon length, like that. Okay. Oh, sorry, I have missed an H. Okay, so this is, you're calculating the mean of the exon length for each of the groupings. Okay. We'll see how it looks like in a second, but I'm going to do another one. You can do as many summaries as you want, and I'm going to do standard deviation as well. SD length equals to SD exon length. Okay, I'm just going to do 2, and then you get the idea, and we'll see how it goes. I'm just going to print this out, not going to save into a new variable, just to visualize this, right? And then run it into console. And what do we see? Okay. We see a much more simplified version of our data frame. Now, each of the samples, the genotypes, has been separated to each of the groups, A, B, C, and within each group, you see a different mean and standard deviation for each group. So this gives you slightly more information on what's going on in the individual groups, and you can make decisions immediately on the type of data that you have. Is it good data? Is it highly dispersed or whatever not? Right. So I do highly recommend using grouping and summary when you're trying to get a better feel of your data. All right. Questions about this part? Is it too complex? Is it okay?
It's okay, but we haven't saved that table, right?
Yep. Yep, you have it. No, yep, you have it. Yep. So let me copy this and put into Etherpad. And I'm not saving this. Again, you can save this if you want to. This is just for summary purposes. So I'm not gonna. It's just for information, just to get a bit of statistics on our data set. Okay? And you can do as many summaries as you want. You can continue with mean of the exon branches, variance of branches, whatever that you want to do. You can do so many things with a combination of grouping and summary. I do.
What is it in the function that makes you have the columns? It's the summarize that gives you a table.
So the summary, this last function is the part that will create the 2 new columns, right? Okay. So it will create the mean length and SD length and whatever variable that you're trying to create. If it's grouped like that, then it will have these factors or these groupings in the first column, genotype. If not, it's just going to give you one value. If you don't specify grouping, it's just going to summarize the mean length and standard deviation for the entire data set.
Right? And how would you save this little table? Would you save it just into a variable?
If you want, then you can do like that summary like that and create a new variable and make sure that you create the assignment operator, and you then save it into that.summary, and then later on you can extract the information out if you want to. Okay, so if you print out that.summary, this is actually a table, and it's the same values as we printed out previously.
Okay, thanks.
Okay. Okay. I'm just going to remove the variable. Again, it's optionals. I did put a link to this particular package called Stargazer. I like this quite a bit because it generates a summary, not for each group. You can sort of like format your data so that it gives you per group summary, but just for the entire summary of your data, it gives you this table that you can easily just publish immediately without any formatting, because it looks very, very nice. It's called Stargazer. Give it a try. If you're doing linear regression and you want to show your model in a table form, this is also very convenient because you have to just provide the model and it lists down all the coefficients and all the residuals in one table in a very nice format. So give that a try, right? Okay. So before we move on into our T-test and Wilcoxon test, I'm just going to mention one thing, and this is also a start of our statistics, the testing part. And I want to mention about testing for normality and variance. I'm going to show you how to do the normality, and then variance is almost the same, different function, but the same idea. Okay. So normality is very, very important because for parametric tests, it has a couple of assumptions. And one of the assumptions is that your data has to be normally distributed. What does it mean? It means that if you were to plot your data points in a graph, you expect to see a central tendency, which is the mean, somewhere in the middle of the distribution, and that the variance or standard deviation or the tails on both ends are more or less equal, right? So you have to make sure your data is normally distributed before using parametric tests. If it's not normally distributed, then you have to move on to non-parametric tests and perform your testing. Okay, T-test is an example of a parametric test. So if you have no reason to assume that your data that you generated is normally distributed, you cannot use a simple T-test. All right. So how do you test for normality? I have two ways. One is by plotting, and then the other one is by statistical tests. Okay, I'm going to do plotting first because this is going to be more visual. You're going to be able to see the plots a bit more, more direct. And I'm going to use again ggplot for this. You don't have to load ggplot. It's part of tidyverse. You can just straight away plot. Recently, I started to use qplots, which is again it's part of ggplot, but Q stands for quick. It does speed up your plotting because you just have to provide a particular variable, like column from your data set. But in our case, we have 3 different groupings, and I want to have more control over the distribution or separation of these values by grouping. So I'm going to stick to ggplot. If you know qplot, it's exactly the same thing, part of ggplot. Okay, again, you can follow along with me, or you can wait for the code at the end of this section, and we can see what the plot looks like. Okay, so we're going to start with our data called det, and then we're going to provide the aesthetic. So it starts with AES, and within this, you can provide your x axis, which variable do you use for your x-axis, which variable do you use for your y-axis. We're going to do a simple density plot. You can do density plot, histogram, ECDF, whatever that you want. I'm going to do the density plot, and the only thing that I have to provide is the values for the x-axis, because the y-axis will calculate the density of your distribution. So I'm going to say x equals to, let's start with exon length first, right? And I'm going to separate the data points by the genotypes. So I'm going to separate by color. So I specify color equals to genotype. Right? Take note that I do not have to provide the variables as parentheses because this is a variable as part of the table. So ggplot understands that this is actually a variable. Okay, this is my static, simple, and I'm just going to do a geometry of density, and that's it. Okay, I'm going to paste this into, I'm going to paste the whole thing, make it easier, into Etherpad, so you can copy and run this if you want right now. And we're going to see what the plot looks like, right? So this is exon length for the three groupings. You can see the central tendency, the mean, is more or less similar to what we got previously, 203 for grouping B and about 400 for A and C. These are prime examples of a normally distributed data set, right? You see that the standard deviation, the spread is more or less equal on both sides. There's no skewness. It's directly in the middle. It is, yeah, there's only one central tendency. There's only one highest peak. This is a very good example. Well, it's good because it's generated by me randomly. But this is an example of normally distributed distribution. Okay, I'm going to try this again with exon branches and see how is it different. I'm going to just type the whole thing properly, but you can copy the code previously and just change the value of X to exon branches, color equals to genotype, and then do geom. Okay, let's do geom density. Density looks nicer. You can try histogram if you want to. You can do whatever, box plot if you want to. You can give it a try. I'm going to do density. Okay, this is an example of a distribution which is not normally distributed. You can see firstly that the central tendency is skewed towards the left of the distribution. And also for another example, I think B, it has these multiple peaks that is going on in the data set. So it's not a normally distributed data, right? So very quickly, you can differentiate these two data set, and by eye, you can make some decisions on your data set. What is the other way to test for normality? Okay, we can do what we call as the Shapiro test. I think Shapiro-Wilk test. I do try to do this often when I do t-tests or do this sort of statistical testing. But if you're confident or you're used to your data set, the kind of values that you actually obtain, you can skip this and make your own assumptions. But with Shapiro-Wilk test, what it does, it tests for the null hypothesis, which is that the population is normally distributed. So it is an example of a statistical test, and the assumption is that the null hypothesis is that the population is normally distributed. So if the p-value that you get from this statistical test is significant, then you reject this null hypothesis. So this is an example of how by textbook, how you generate your hypothesis and make decisions on the outcome, whether to reject or to accept the null hypothesis. Okay? You can also generate your alternate hypothesis if you want, but usually we reject or accept the null hypothesis. Okay. So firstly, let me see. I'm not gonna use the whole distribution. I'm gonna use one, let's say, variable. I'm gonna use exon length, and from the genotype A. Okay, I'm gonna use that. So I'm going to create a new variable called A exon length to represent the values of exon length from genotype A. And I'm going to use a subsetting which I don't usually teach or I don't usually use, but it's very simple because it's just one line. Well, simple because it's just a simple code. I normally use tidyverse to kind of like extract values, but this is just very quickly just to extract these values. I'm going to type it first and I'll show you what it does. Okay. So this is the function. It's actually make up of the name of the data set, that, as well as the square brackets. So square brackets in R refers to the dimensions that you're trying to subset. Basically, which rows do you want to, basically, sorry, I missed out something, equals to 8. So basically, which rows do you want to select, and which rows do you, which columns do you want to select? Right? To specify the rows, you specify some sort of like true, false, some sort of Boolean values before the comma sign. And then for columns, you specify, you can specify the index of the column or the name of that column after the comma sign. So anything before comma sign is for rows selection, after comma sign is column selection. Okay? If you were to run this just on its own, like that, it's going to generate a true false statement, like the same way that you actually do for tidyverse if you want to filter your data set. Right? So these are all just basically true false. And what this does is it will select rows which returns true, and those which are false will be removed. Right? And then we specifically select exon length, which is the second column on this for this data set. So I already pasted the code in Etherpad, so you can copy this and run it. And I'm just going to quickly check that exon length is now no longer a data frame, but it's actually now a vector, right? So it's a vector made of 1,000 values, and these are all representing the length of exons from sample A. Okay, so let's go straight to the testing. Shapiro test. The function is Shapiro.test. It comes prepackaged with R, and the input is simply the variable that you are trying to test. So in this case, a.exon length. You copy this code to Etherpad, and you can run it together with me. Let's run this and see what do we get. This is a typical output of almost all statistical tests that you do in R. You will have some sort of description of the test that you perform. In this case, it's Shapiro-Wilk normality test. Sometimes they will tell you the data. In this case, A.exon length. If you are comparing between two data, they will tell you what is X, what is Y. They will calculate some sort of statistics. In this case, it's the W. This is the, so different sort of testing use different statistics, like T-test use T statistic. ANOVA use F statistic. So this is, I think this is Wilk statistic, I think. So the value that you get from that statistic, that computation, is 0.99851. But more importantly, you get a p-value, which is the confidence value for that particular test. And in this case, the p-value is 0.5619. So what do you do with this p-value? So you can use this p-value to make your decision on whether or not to accept or reject the null hypothesis. Usually you will set a cutoff of about 0.05. Anything lower than 0.05, you will reject the null hypothesis. This value of 0.5 is dependent on case to case. So if you have reasons to believe that you want to have a higher confidence value, so you want to have, let's say, 99% confidence level, you can reduce this to 0.01. That is at 99% confidence, and you can reject or accept based on that particular threshold. In this case, the p-value is 0.56, meaning that we fail to reject the null hypothesis, and which then means that our data is normally distributed. All right. So conclusion from this particular testing is that this data A for exon length is normally distributed, which we know from our plot previously, and statistically it is also shown to be to be normally distributed. Okay. The only thing weird about Shapiro-Wilk test and some of the other tests for variance is that if the p-value is above 0.05, it's a good thing. So when I first did this, I was like, I got confused because we tend to be happy when the p-value is lesser than 0.05 or 0.01. But in this case, you want it to be above 0.05. All right. Again, the reason why we are happy with this value is because the null hypothesis is as such. is that the population is normally distributed. All right. Questions about the Shapiro test before we move on?
Are there going to be other options to just do like a normality test on things quicker, like all of, for example, the 3 different columns or something like that?
Yes, this is what I'm going to get you to try
Okay.
in a bit. So using the grouping and summarize, right? Well, I wouldn't say quicker, but it will give you detailed information. So I understand you like, I don't want to copy this 6 times for each of the different variables and do Shapiro test. So you're going to try this Shapiro testing for each of the variables in a bit. All right. But before we do that, I want to show you how to extract these values. So this is fine. This sort of description is fine, but sometimes you want to just get certain values. So how do you do that? Right? I'm going to repeat the Shapiro test, but now save it into a variable. Right? I'm going to call it Shapiro A, for example, A.out, for example. You can name this anything you want, doesn't really matter. And I'm going to run this. Instead of displaying the result, it's just going to save the values into the variable Shapiro A.out. And what you can do now is that you can extract these values by using the same $ that we have used. So if I do Shapiro out dollars and wait for the options, RStudio will give us several sort of sub values or higher level object values that you can actually call out. For example, the statistic, this is the 0.99851 statistic that you generated. P-value, method, and the data name. I think this is the A.exon length. So whatever that you see here can be extracted. And then this is inconvenient because if you just want the p-value, you can extract this value like that, $p-value, and you get the value of 0.5619 as it is. Right? So imagine now you can do groupings and summarize very quickly and just obtain p-values for Shapiro test, and you can make decisions on your data very quickly. Okay, and this applies again to almost all testing that we will be doing in our T-test, ANOVA test. We can use this extraction $p-value for extracting the values. Okay. So I think it's a nice, okay, it's 10:53. I think what we're gonna do is we're gonna go take a quick break, a 10 minutes break. In the meantime, if you want to try exercise 2, you can give it a try. I'm gonna paste exercise 2 in Etherpad. So what I want you to do is to calculate the p-value of for the different groupings and for the different variables. So for exon length, what is the Shapiro test p-value for each of the groups, and do the same thing for, sorry, I gave the answer. I hope nobody sees that. So I do the answer, and at the same time, what can you interpret from the data that you get? Okay, so what you can use is you use the grouping by that we have done for the mean and standard deviation, and just change the function to use. So instead of mean, use Shapiro.test and extract the p-value for your different tests. All right. And then now time is 10:55. We'll go for a 10 minutes break. We'll be back at about 11:05, and we go straight into all our T-tests and ANOVA tests. All right, I'll see you in a bit. All right, time is now 11:05, and I think we better resume our workshop. So I just finished typing the answer to exercise 2, and I've already pasted the answer as well in Etherpad. So if you want to run this code along, you can go ahead. So as mentioned, it's the same exact function as previously, and you can see how powerful these grouping and summarizing functions are. Just instead of mean, I replaced mean with Shapiro.test, and I calculated for exon length as well as exon branches, and I created new new columns called Shapiro.length, Shapiro.branches. The only difference is that now I extracted the p-value directly from the test. So after the test, like that, instead of just printing out the entire statistic, which you're going to get error because it doesn't understand, it's expecting a value, not an object. So instead of just printing out the entire thing, I specify that I want the p-value, and this is what we get from the output. For Shapiro length, all of the p-value is above 0.05. It's all normally distributed. But for Shapiro branches, these are all lower than 0.05. So we reject the null hypothesis and conclude that branches are not normally distributed. Right. So this is the interpretation of the data and how you perform this very quickly.
I almost got
Yep.
that, but I didn't know where to put the dollar p-value.
Yeah.
I put it before the bracket.
I see. So if you put this before the bracket, then you are trying to specify the. It's what it's trying to say is that this p-value is part of exon length, which is not. It's actually part of the output of Shapiro test. Yeah. If that makes sense to you.
So to remember, basically, you always have to, because I understood that, like, if you want to put it into a table,
Yep.
you can't put the whole test, but you need to put one element of the test.
Yep.
So you always have to do the dollar and then whatever variable you're looking for, like, afterwards, basically.
Yep.
Yeah.
Okay. And the value, the variable has to be present in the test.
Yeah, of course.
P-value should be universally used. Yeah. But some other statistics
you're like calling for a variable that's part of the output of the test.
Yeah. Exactly. Okay, cool. All right, so let's go straight into our one or two sample tests, right? And I'm gonna break this down into two parts. Let me just quickly give some space so we can see my screen. I'm gonna separate by parametric tests and non-parametric tests. Okay. So assumptions, as mentioned, there are a lot of assumptions for parametric tests. I'm going to type this out and explain. Number one, data has to be continuous. Right? If you have, you cannot use, again, ordinal nominal data for this. Even discrete, if it's not normally distributed, you cannot use parametric tests. It has to be independently sampled. That means the sampling method for each of your groupings do not affect each other. That way. It's usually fine for us, but for clinical data, that is a bit more sensitive. You have to know exactly how the data was obtained. We already showed how to test for normal distribution. All right, number 3 makes sense. Number 4 is reasonably large sample size. Usually it's about more than, for t-tests, it's more than 10 for each of the groups. But then there are ways to actually calculate this. I'm not sure. I was taught this a long time ago. Like there's a formula they can use to calculate the ideal sample size, but I've never practiced it. So if you know of such tests, go with that way of determining sample size. And then lastly, homogeneity of variance. So this basically means that the variance, the spread of each of your groupings are more or less the same, right? So in this case, it does look very similar, the variance. I think we also tested variance a little bit previously. I'm not going to show you how to do this, but I'm going to paste a way to test for variance using a package called CAR. Okay, it's very similar. Idea, you test for p-value and you reject the p-value. Sorry, you reject the null hypothesis if the p-value is 0.05 or lesser. And but same thing as Shapiro test, if it's above 0.05, it means that the homogeneity the variance is homogeneous across all your samples, right? Give it a test if you want to quickly test your variance for each of your samples. All right. So this is parametric test. For non-parametric test, there's no need for any of these assumptions. If your data set doesn't satisfy all of these conditions, assumptions, you have to go straight into a non-parametric test. Yeah. So we're going to
Fresh, I'm sorry.
Yes.
Question again. Sorry, it's always me.
No worries. No worries.
Isn't homogeneity of variance? Can you even have a sample which is normally distributed but does not have homogeneity of variance? Isn't it kind of part of the test?
No, not really. For if you're doing two sample or say one sample test, it's actually not part. The variance is actually not part of the requirement of the test.
No. Sorry, I'm saying you're saying as a requirement we have to look at the homogeneity of variance of our of the sample, the data we're checking. But if we do the Shapiro-Wilk test or other normality tests, isn't that covered, the homogeneity of variance?
No, it's different.
It's different? Okay.
Shapiro just tests for the normality, right? But it doesn't tell you whether the variance is homogeneous. Meaning, for sample A, B, and C, is the spread between these three samples more or less the same?
Okay.
Right.
Yeah.
So it's a separate thing.
Okay.
And okay, let me give you a bit of like heads up. For example, if you're doing ANOVA, right? There are two types of ANOVA. You can assume that the variance is equal, and you go with one type of ANOVA testing. If you have reasons to believe that the variance are not equal, you have to use the testing for unequal variance, which is slightly different model, right? So knowing your variance will actually determine what sort of test is more appropriate for that particular data set. Okay,
sure. So we have to basically, we have to test for normal distribution as well as the variance test.
Yes.
Okay.
Yes. Right. Again, for parametric tests, okay, if you know your data is not normally distributed, or if you want to go with non-parametric tests, you don't have to do any of these assumptions to begin with.
Yeah.
Okay, cool.
Is the Welch test, is that for variance?
No. So the test for variance, I've already pasted in the lesson code. It's called Levine test. I'm not going to use the Levine test right now, but you can try test for homogeneity when you want. I'll give you an example of how to test for Levine test in the Etherpad. Okay. All right. So in our case, this distribution is normally distributed, as well as the variance is more or less homogeneous, and I've tested this before, and it's really homogeneous. Okay? And let's start with the Welch T-test. This is just a simple T-test, and we're going to compare the means between exon length between two groups. Okay, let's say A and B. Let's set up our null hypothesis first. Again, always nice to have like an idea of what is the null hypothesis, and later we can accept or reject. So the null hypothesis is that the mean length in samples A and B are equal. Okay, so this is a typical null hypothesis for testing of means. Right, so t-test is an example of testing for means, and it's, I guess, from your check-in, a lot of you use t-test very often, which is, it's a great test, a simple test. If you have just two groups, or even one group, I'll show you how to do one sample test and replace the second value with a certain mean that you want to test against. First, let's create our two vectors, exon length for A and exon length for B. You can copy again whatever we did previously, the A.exon length, you can copy the same thing. I'll probably do that. So you have this created, and then do another one for sample B. It sort of saves a bit of time, and make sure you run these two code in console so that you save all of these files, all of this data in a variable. Okay, cool. So t-test, function for t-test is very simple. It's just called t.test. And there are several arguments to this. Let me see, maybe I should bring up the help vignette so that you can see some of the arguments. You can see, bottom right corner, you can see the vignette for t-test. So pay attention to the second method. So you have to provide your x, which is a vector for the values that you want to test for, which, for example, in this case would be a dot exon length, which is 1. If you have another distribution and another values to compare against, for example, b dot exon length, then you put y equals to that particular value, right? So this is what I'm going to do, like y equals to b dot exon length, like that, okay? Before explaining the other variables, other inputs, I'm going to run this first so that we can see what is the output. So if I run this without saving into a variable, you get the same sort of description that you get as the Shapiro test. You have different t statistics now. This is 87.112. So if you're not sure what this t means, if you recall your statistics courses when you are in your undergrad or doing masters, there's this table whereby there's this this normally distributed curve, and on the x-axis you have different confidence interval, and then there's this another table with with one column with degrees of freedom, number of samples, more or less, and then the confidence interval that you're trying to test. And for each of this combination, you have a t value, a t statistic. So this is exactly what it is, based on our degree of freedom and our confidence interval, which is currently set to 0.95. The t statistic is 87.112. And then you use this t value to go back into the normally distributed curve, the t table or t graph, I think it's called, and then figure out where this 87.112 is in this in the curve, and whether is it above your threshold for your confidence interval or confidence level, right? So this is just the value that you extract from that particular table. Then you have your degree of freedom. In this case, it does look a bit more than I expected though. Usually it's 999, probably it's 2 samples probably. And then you got your p-value. You know? For R, if your p-value is below 2.2 power of 16, it will convert it into this particular annotation. But if you extract this value, the p-value from the extraction, you will get a more accurate value. Right? If you get value of 0, means that it's really 0. It's like the lowest value that you can get for that particular p-value. Right? And what else do you have? You have your alternative hypothesis. You have your confidence interval, 95% confidence interval, and then your mean estimates for x and y. This is simply calculated by using mean. All right. Okay. So you can extract p-value right now if you want to. For example, if I were to save this as a t-test dot out, too much t, like that, and run this code again, I can get the t-test statistics out. I can get p-value, for example, confidence interval, all the estimate directly from here. I'm going to try p-value and show you that in this case, it's a value of 0, means that it's that's very, very low p-value for this comparison. I do have this tendency to display exact p-values. Some publications prefer that based on my experience. So this is the p-value that you want. If you are more confident or more familiar with the range with the asterisk, so annotate less than 0.05 or say 1 asterisk, for example, you can go ahead and just set your confidence interval as such. Okay? So we can change some of these parameters. I'm going to just copy this and rewrite it again. So what can we change for this particular test? We can specify if you want to do a 1 sample or 2 sample test. So previously we did a 2 sample test. We compare exon length between A and B. if you want to compare the exon length of A with a particular value, for example, your hypothesis is that you're testing whether the mean of exon length for sample A is different from 300 micrometers, or the value of 300. So you're not comparing with another sample, you're comparing with a known mean. This is sometimes useful because sometimes you want to test whether a distribution is above a particular value. Like, is there a value, like is it more than 0, for example? So to do that, you specify mu instead of y. So mu is the mean that you're testing against, and I can do mu equals to 300, and this will compare the mean of x, or A exon length, with the value of 300. So this is how you do a one sample t-test. Right? You can also change the tail of your testing. So I'm going to quickly write this first. Let me do a two sample y equals to b dot exon length, and I'm going to do a instead of a two-sided test, which is the default, but the default t-test is, it assumes that you're testing for two sides. It can be above, say B can be more than A, or vice versa. Or you can actually specify that A is less than B. So to do that, you specify the parameter of alternative into one of the three options. So it's either two-sided, less, or more. I think that one is more. Let me just quickly, greater. So it's two-sided, less, or greater. So this is based on the assumption that your hypothesis that you created. All right. So this is what you can do. I'm just going to continue on and do a couple more stuff so that you can see everything in one go. You can, if your samples are paired, right? Both of your two variables are taken in a way that they are, again, paired. I'm pretty sure you understand what the pair is. You can set paired equals to true, and this will use a different sort of model to calculate your p-values. And a couple more, if you have reasons to assume that your variance is equal. In our case, it's actually equal, actually. So we can actually set this to true, like that. And this will give you a more refined, p-value with assumption that your variance is equal. And then last but not least is your confidence level. You can set this to 0.99 if you want to. I don't do this so often, mainly because the p-value that you get here is representative of the confidence interval that you are expected to get for this testing. So I base the results on the p-value that I obtain rather than the confidence interval. But this is just a estimate of your range that you're trying to test. Okay. Meaning that even if I set this to 0.95995 or whatever, the p-value will still be the same. It's just that what is the threshold that you're trying to set. Okay. Cool. Questions for t-tests?
Yeah, okay. So you did a one sample, and then you did a two sample, and then you went back to the two sample, but you're adding more options.
Yeah, this is just an example. I'm just giving you
What's
different.
the alternative equals less again? Sorry.
So this is trying to test whether so initially, without, by default, this is a two-tailed test or two-sided test.
Oh yeah,
so in two-sided test, you assume that the mean can be above or below. So A is above or below of B, for example. But if you specify this as less, then you are specifying that A is less than B, or greater than B if you assume that it's greater. This is, in terms of p-value, this is going to be better because your degree of freedom is lesser, and therefore you get a better p-value. But if you have no reason to believe that it's actually one-sided, you should just go with two-sided, and which is usually what we do in t-test. We assume that it's two-sided sort of testing. Okay, and then the rest are different parameters that you can actually tweak if you want to refine your test. Okay, cool. So for non-parametric tests, if these assumptions above are not met for your data set, for example, for exon branches, it's clearly not normally distributed. I think variance is more or less the same, but it's not normally distributed. So we're going to use a non-parametric test. And the test that I'm going to use is called, there's different names for this. There's Wilcoxon rank sum test, Wilcoxon signed rank test. There's also Mann Whitney EU test, but essentially the models are all very similar, right? And the way you actually perform this test is also similar. So I'm going to start off with creating variables first. I'm going to create variables for exon branches, exon branches. Yeah, the thing is you have to create a new vector for every time you do this, because the input for the t-test and Wilcoxon test are vectors. So I'm going to do $genotype equals to A. You can copy the stuff above if you want to. I'm just going to run exon branches. What's it, branches? Yeah, B dot exon branch.
By the way, I think Wilcoxon is mostly like Mann Whitney is your 2-sample t-test non-parametric, whereas Wilcoxon tends to be used more like for the non-parametric 1-sample t-test.
Yeah, there is also a name for 2 samples. So for 1 sample, it's Wilcoxon. Was it sign rank test?
Well, they both call them signed rank because that's just the method.
Yes, it's just a specific name for that particular method. Yeah, so it depends on. I typically use Wilcoxon in almost all these names I use for publication.
I use Mann Whitney for the if you compare two samples, non-parametrically, usually it's a Mann Whitney.
Yes, but I've also used Wilcoxon rank sum test as a name to specify that this is 2-sample non-parametric test. And even if you sort of like look at discussions and stuff, everybody knows that this is exactly the same thing. So I guess it's just specificity in terms of what you prefer. You prefer to call it Mann Whitney, because it generally in statistical field, we understand that this is non-parametric for 2-sample. So let's see. Okay, so this is, let me also paste the code over in the lesson. I'm gonna paste, I paste this? I'm gonna paste the whole thing, the Welch test. And yep. So I've created 2 new vectors for exon branches, and for both A and B, this should run okay, unless I'm getting, yep, they should run fine. So similar to t-test, the name of this test is very simple, Wilcoxon test, and you specify the 2 new vectors that you created. So A.exon branches and B.exon branches, like such. I'm just going to put Y equals to be specific that we are specifying that this as Y. And I'm going to run this first before I show you the parameters for this Wilcoxon test. And you can see that the p-value here is 0.1735. Before that, the null hypothesis is that the mean of exon branches between samples A and B are equal, right? Okay, so p-value here is above 0.05. So we fail to reject the null hypothesis, and we conclude that the mean number of exon branches between these 2 samples are equal, right? So this is the decision. Let's see what does Wilcoxon test have. It has almost the same parameters as t-test. So you do have the option to specify mu. So you can see my screen on the bottom right here. You do have mu. You can set, if you don't have y, then you have to specify mu, which is the mean that you're trying to compare against. You have the sided test, whether you're 2-sided or 1-sided test. You can test for whether or not it's a paired sampling. There's confidence interval as well, 0.95. A couple of these I'm not very familiar. confidence interval. Probably this is a whether or not to apply continuity interval. Okay, so whether or not you apply additional model to your testing, and exact whether or not it's false, whether you want to compute the exact p-value or a non-exact p-value. I guess it's some sort of range or something. So that is.
By the way,
yep.
for the null hypothesis, I think it's more, it's testing if the median of the axon branches between samples A and B are equal. Because it doesn't use a mean.
It doesn't yet. You're right. You're right. I typically when I first did this, I thought it was median testing, but the more that I search on this field, the consensus, well, maybe for our studio, for R, it does use median, but for the general consensus in the statistical field, mean does come up quite often as well. I know that it's not accurate to do mean, because since your data is not normally distributed, you have outliers, so the mean is very prone to this outlier. The mean actually change with these outliers. But somehow, I do still get people mentioning about mean when we compare, when we use Wilcoxon tests to compare means. So I would say, yeah, probably mean/median, depending on if you're using exact calculation, exact model, then you can specify mean or median. But I think for this, if I'm not mistaken, I'll check with you whether is it in R is it using mean or median, but it's always interchange. I sometimes feel very awkward about the specificity of these tests.
Okay.
Okay. So far, everybody okay with the T-test and Wilcoxon tests? Any problems with getting, let me paste this first. Any problems getting the output for Wilcoxon tests and T-tests? Okay, cool. So let's go ahead to the next part. We are running a bit of time. I'll play around with what's important and see what I should show you. All right. This one is very important. I'm pretty sure a lot of you have want to test between more than 2 samples, right? So same thing. There are parametric tests for this and non-parametric tests, right? So very quickly, the parametric test is ANOVA, right? This is analysis of variance, and the non-parametric test here is the what's it called again? The wait. No, is it? Oh yes, Kruskal. Yeah, always forget it. Kruskal Wallis test. Right? Okay. So with this, what you're trying to test is for ANOVA whether the means between your 3 groups, is there any one of the groups having a mean different from another, right? So typically your null hypothesis is that the means, let's say in this case exon length, of exon length in all 3 samples are equal, right? LNGTH. See, I'm also making the same typo, Katrina, so it happens. So we are testing whether in any one of these groupings, any of the samples, whether the means are different from another, right? It doesn't tell you which, for ANOVA, it doesn't tell you which sample is different, but you can do post hoc tests later on to compare and determine which sample is the one that is deviating from the other. All right. So let's go straight into the functions at ANOVA. if you sort of search for ANOVA testing in R, you have two flavors. I'm going to show you the first one because the first one allows you to do post hoc tests quite easily after that. And it's called AOV, analysis of variance. The input here is slightly different. If you see, the first input is actually not X or Y, it's a formula, right? So the formula is based on the data that you have provided. So data here, I'm going to just quickly write data equals to that. This is the original data. But the formula is basically what is your predictor and what is your outcome. Okay? And when you write formula, it's always the outcome first, followed by your predictor. So your y-axis, if you think of it as a graph on a Cartesian plot, it's your y-axis first, what's your output, and what is your x-axis is your groupings. So in this case, we're going to write it as such, exon length. And to sort of do this formula to comparison, you need the tilde symbol. If you have problems with this tilde symbol, I'm going to paste the code for you in a bit, so you can copy the tilde sign. And then this is followed by the variable on the x-axis, which is genotype. So I'm going to copy this for you. Let me just copy the whole thing into the Etherpad. And let's see what this brings us. Okay, cool. So this is the output for the AOV, analysis of variance. It gives you the degree of freedom, some statistics that comes out from the test. This is F statistics and some residuals and some sort of standard error. One thing that you are missing here from this output is the p-value, which is usually what we are trying to look for. Weird thing with AOV, this particular function, it does store the p-value, but it stores it somewhere else. I mean, deeper, it doesn't show you the p-value. So let's extract this p-value out. I'm going to save the output of this ANOVA test into a variable called AOV.out. You run this again. And then I'm going to do, you can do p-value right now, but I'm going to do a summary of AOV.out. And here is where you can find the p-value for your analysis. It's actually on the last column here. And it again says that the p-value is less than 2 power negative 16. And it's in terms of the asterisk coding for this particular p-value, it's highly significant. Okay. I haven't tried this, but let me see if AOV.out does generate p-value. It might not. Probably in one of these. It doesn't have this p-value directly. I think some weird output that, so it's not here. So the only way to kind of like determine the p-value is to summarize the output of this AOV.out. This is the only way that you can sort of see. I'll check out if this, I know this particular output can be sort of like disassembled and you can actually get individual values as a table, but it requires a different package called Broom. So I'm not going to go through that, but generally you can still get the p-value from just summarizing this. Right? And then you can sort of like make decisions from there, right? So for AOV, let's see what other arguments are there for AOV. So we have, again, formula and data has been covered. These are, again, things that I don't use normally, projections and contrast. Contrast can be used if you have, in a particular group, you want to specify which of the groupings that you want to compare. So A and B and stuff, you can actually do this directly. And these are projections and return. I am not entirely familiar with what these values refer to. I don't usually use them so often as well. So I guess the only thing that's important here would be data and your formula, and you will get your statistics directly from the output. All right. So going to share with you how to do a post hoc test for ANOVA. Oh yeah, before that, this ANOVA test, let me see if it does say over here. This ANOVA test specifically assumes that the variance between your groups are equal, right? In the other function I'm going to show you in a bit, there is an option to specify whether the variants are homogeneous or not. But for this particular one, this inbuilt AOV test, it assumes it's equal. So if it's, if you have reason to believe that your data is has equal variance in the different groups, then this should be fine. Okay. As mentioned, the reason why I use this is because I want to show you the post hoc two-key test. And this is, again, useful if you want to figure out which of your 3 samples are different from the other. Right? So this will do some sort of, it's not directly pairwise t-test, but it's a specific test to test in between 2 samples. Right? Let's try this out. Right? Function is two-key HSD. HSD, I think, stands for on a significant differences. And the input is the output of the AOV, and the ANOVA that you've done previously. And that's it. All right, I'm going to run this, and let's paste the output into Etherpad. And what do we have here? We do have a pairwise comparison between the different possibilities, B versus A, C versus A, C versus B, and you have the same sort of more or less same statistic. This is the difference, I think this difference in means, and then this is the upper limit and lower limit of the confidence interval, and this is your p-value. This is adjusted because whenever you do multiple testing between, in this case, we're comparing three different individual pair tests. Instead of just showing you the raw p-values, is adjusted so that it gives you a much more accurate p-value. Yeah, I think this should be Bonferroni, I think, or probably the other one.
You've got like false discovery rates.
Yeah. The other one is the more common one. How do I put the name now? FDR. FDR. Yeah, you're right. FDR. False discovery rate. It's either these two, but they are very similar.
You've got like you've got Dunn's multiple correction.
Yep.
False discovery rate, which has a lot of different ones, and then you've got two-key and Bonferroni.
Yep.
Those are the most common.
Yep. These are different flavors of multiple testing that you can actually do. Probably mention here what sort of in two-key, or we can read through what sort of correction they perform. But this is what you essentially want, a corrected p-value when you do this sort of test, right? Other alternatives, I'm not going to run this. Probably just going to type this and then let you try. This is pairwise t-test. This is also come inbuilt with R Studio. So this gives you similar statistics, but the way they test is different because they're doing pairwise t-test between your different groupings. So you can try this out and see what sort of post-hoc test you want to perform for your analysis. Okay. Let's see. What about for nonparametric? So Kruskal Wallis test is the key or the go-to test to perform this, and it's exactly similar to ANOVA in terms of how you perform this function. Name of the function is Kruskal.test as such, and the inputs are, let me see, it's the same formula, but if you have a different way of if you provide as a vector, it can also accept vector. So there's also a formula and a data. So I'm going to use this method. If not, you can provide X and G. Basically, X is a numeric data, so basically the entire column. But at the same time, provide G, which is the groupings for each of these value. So you have to provide 2 vectors if you prefer to input vectors. I'm just going to use the same formula as previous, just instead of using exon length, we're going to use exon branches. And against genotype, and data is equals to that, right? And let's see. Right. Yeah. So this is very straightforward output. There's p-value, and p-value will be captured as a data for this particular output. You can extract this value. You have the chi-square test, the degree of freedom. You have 3 samples here, so it will be 3 minus 1 degree of freedom. And this is the value that you get from the for these rank sum tests. Okay. Again, very straightforward way of testing. There is a post-hoc test for this. It's called done test. Is also it's called done test. I think DUN test. Probably there's another package for this. There's a different package for this. I don't have this yet, but I'm going to paste this into, or the link is already in Etherpad. So if you want to look at done test and how to perform this in R, you can go ahead and give it a try. But again, the idea is very similar. You're just testing pairwise, doing pairwise testing between each of your groups and test whether each of these any of these groups are different from each other. Okay. There are also other variations of, let's say, ANOVA. Previously, we mentioned that if we have a different column for, let's say, time points. So let's say we have different time points and we're comparing, let's say, treated, untreated, or 2 different genotypes for each time point. Then, just a simple one-way ANOVA will not do. You need to have a different model to calculate statistics. So I'm just going to quickly mention a few, and then the links are already in Etherpad. So one is called two-way ANOVA. Right? This is where you have your individual groupings. Let's say, use a different example, because if you do time points, it makes a bit more sense. So if you have 3 different time points, all right? So you have a value for each of these time point, and for each time point you have 2 different genotypes or 2 different treatments, right? So then you can actually do a more specific test, a two-way ANOVA test, to test for whether or not any of these groupings are statistically significant from another, right? So this is very specific for another layer of groupings, if you want to think of it that way. Okay. And then you also have MANOVA. So this is multiple variables. So as of now, we look at just one variable, exon length. If you want to test more than one variables at the same time, you can also do so using MANOVA. Check the assumptions for these 2 tests. There could be a couple more assumptions. For example, they could require that each of these variables or these groupings have equal number of data points. So do check what are the specific assumptions for this different sort of test. Okay.
Sorry, I didn't hear you for the two-way ANOVA. What did you say the example could be?
Okay, so think, for example, you have 3 different time points, right? You have 3 different time points, and you're measuring, let's say, exon branches for 3 different time points. Right? I can pull up some example from. Let me do this. Let me show you a example from. So if you're not sure, like if you want like a example or a resource to kind of like do a lot of this statistical testing, I do recommend this STHDA website. Let me share this with you. Yep. Okay, can you see my screen? Okay. So this is the typical example that you have for two-way ANOVA test. So you have time points or let's say dosage. In this case, you have 3 different dosage, and within each of these groupings, you have subgroupings. So this is supplemented by 2 different treatments, I think. So in your case, could be a genotype, could be treatments, and you are trying to test, whether the difference between the groupings are statistically significant or not, right? There will be post-hoc test because this is ANOVA test. It's going to test, like, generally give you a p-value for the entire data set. There are post-hoc tests that you can actually do to determine which of these groupings are different from each other, right? And this is one example of a two-way ANOVA test.
Okay, thanks.
Okay.
So it's basically, yeah, so it's 3 different doses on 2 different populations.
Yeah. So there's a subgrouping to it. So instead of just one variable, or like one categorical variable, you have 2 different categorical variables to test by time, also by dose, right? By dose, in this case by dose, or by the treatment. There's also a way to kind of figure out whether the difference is more significant at which categories. Is it changing by dose, or is the in this case supplementary, is it different, more significant as compared to dose? So which variable is more dependent on the change? So there's different ways of doing it.
So couldn't we also do like a linear model analysis, which has different variables in it? So like, is there a scenario where a two-way ANOVA would be better versus doing like a linear model analysis?
Okay, so I typically stay away from linear models for now, for my work, because usually when you have a linear regression, what you're trying to do is you are trying to generate a prediction model that you can use for application. So you have a data set and you want to use that particular formula to predict what sort of values you get if is given a different a new value. All right. If you're not doing this sort of prediction model, right, this very simple test is much more powerful because it has it's well, I'm not sure how to exactly explain to you in terms of like the details, but it's using a model that has in this case some assumptions, and generating a p-value based on the data that you're generating. So put it simply, if you are doing a prediction on your data set, then a linear regression or logarithmic regression, that is your go-to, right? If you're doing some sort of correlation test, some sort of statistical test, okay, put it as a statistical test, then stick with like an ANOVA, a correlation test, a T-test. That is the go-to. Another thing is that with linear regression, you do have to make sure that your variables are suitable, right? For example, on it doesn't have to be strictly numerical or continuous, but it has to have, on the x-axis, it has to make sense that you can actually extract information or predict an information from the particular linear regression. Number one. Number two, the p-value that you get for a linear regression is different interpretation-wise from a statistical test. Right, so for linear regression, you have the R-square value, which talks about fitting, and the p-value, which is the dependency of that particular variable in that formula. Right? Whereby for a statistical test, it compares in this case, the means or testing for variance or testing for median in difference between different groups.
Yeah, they are actually quite different things.
Okay, I think that makes sense.
Yeah. So
Thank you.
So no worries. Yeah, I did came across one point of time, like when you start to kind of like do the statistical test, and you see online like what kind of like what people do, and linear regression seems to be very popular. And I was like, why haven't I used linear regression before? And the reason is because I'm not doing any sort of modeling, so I don't need to use that. And it's always better to use statistical tests rather than regression if you want to compare between your data sets or testing from difference in means and medians. Okay.
Okay.
Cool. Okay, I'm running a bit short of time. I apologize for that. I totally thought that the first part is going to be very quick, but I think it requires a bit more attention than I expected. Okay, let me see. Okay, I'll show you one more. Do you prefer to look at categorical variables, how to compare categorical variables, or do you prefer to do correlation test? Just shout out if you have any preference for this. I will give the code for both, just that I'm going to show you one instead of the other.
I'm almost wondering if if we should have another session at another time.
I'm okay. I'm down next week if there is a Zoom meeting room. If you are available, I can say schedule another one just to complete, and then probably I can add in linear regression as well since we have a bit more time.
Yeah,
I can do
I
linear
might prefer
regression.
that because I have to go.
Yeah,
but it's up to other people can choose.
Okay, so basically in the chat, give like either one of these options. Either you specify the test is either let's put it as correlation test, or I call it Fisher's test, or next week. So 3 options: correlation test, Fisher's test, next week, so that I can have a few. It's not a very big crowd actually, and I think generally we have done quite a few, and you see the recurring pattern here. You see that there are specific tests for it. You specify.
Where do you want us to put this? Like on
chat.
the Etherpad?
Put it in the chat.
Oh, in chat. Sorry.
That's fine. So that
okay.
Will be much more.
Yeah, I'd really love to go through it properly next week.
Yep, that's fine. So Catalina wants next week. Yep. So Shinya next week as well. So I guess that's more than, I need one more to see if it's majority. Again, even if it's not next week, I will share with you the data. Yeah, no worries, Pat. We can record it and give us a second session, like a part 2 to this, and then you can have a look at the code as well as the video if you want to. Adam as well. Okay. Sure. Then we'll do next week. I will try to get a Zoom meeting room again. We'll do same time. I should be fine next week. I shouldn't have anything morning. And then we'll go through categorical variables. So currently we're looking at numerical variables, right? So then it would be also useful to do a testing for independency, whether 2 different categorical variables are independent from each other. And then correlation tests, I think that's also very common. Look at the pattern, you correlate between, let's say, gene expression and protein expression. I've done that quite a bit of time. See whether is it statistically significant. And then I will fit in a linear regression. I think linear regression is fun to do and sort of predict if you do it right. I might use the Stargazer package that I mentioned in the early part of the lesson, because that formats the output of linear regression model very, very well. So then we'll settle as that. We will stop for now, and then I will let you know on the Zoom meeting room for next week. And for those who can make it, I'll see you next week. There's a feedback.
Thank you so much.
No worries. There's a link to feedback if you want to give a feedback for this class, or you can do it next week if you are attending next week's class, so that I can sort of improve the way we do things with our workshops. I think it'll be very valuable.
Okay, thanks. Have a good day. Bye-bye.
Yep. You too. Thank you.